Hello and welcome back. Today I want to continue talking about the basic transistor configurations by looking at the common emitter amplifier. I will try to design such a circuit and then analyze the main features in the circuit simulator. LT-Spice, of course. So if you're curious, then keep watching. Of the three main configurations, the common emitter is the one most widely used. You will see it in all sorts of analog circuits, starting from low frequency signal amplification, like in audio, all the way up to the gigahertz range RF. And at the same time, you will see the circuit also in digital switching applications, where it is commonly used as a load switch. And there are of course other applications. So what makes it so special? Well, the main highlight of this type of amplifier is that unlike the previous two that we've looked at, the common base and the common collector, this circuit is capable of amplifying both voltage and current, offering the highest amount of possible gain of the three basic configurations. But is there a catch? Now, the basic idea behind the common emitter amplifier is that the emitter is kept at a fixed point. Sort of. You will see two main implementations. One in which the emitter is actually kept at a fixed voltage, either directly at ground, or AC stabilized at a different voltage using a capacitor, or you will see it having a resistor connection by itself. Now, the choice between the various arrangements will have to do with the exact value of gain that you want. And of course, you have a mix of the two versions. So, split the single resistor into two different bits, one which is stabilized with a capacitor, and the other one which isn't. Here you get the best of both worlds. The full value of the resistance, so the sum of them, is useful for the DC operating point stabilization, and then when it comes to AC signals, you can have a very precise gain control by adjusting the exact resistance distribution between the two elements. But to get a better picture of what sort of effects can appear, let's start to design such a circuit. So for today, I will be using the BC857C and I will be using a supply voltage of 10 volts. Now, to prevent an overheating of the transistor, I will set a DC operating point around the 10 mA point, but the exact collector emitter voltage is to be determined. So I will use the classical 4 resistor arrangement, and for stability, let's set the 1 volt voltage drop on the emitter resistor. By going through the numbers, this gives us a value of 100 ohms for this particular part. Now, other than this emitter resistor, I will also be using, in parts of our test today, an extra emitter capacitor in parallel with this. Now, for the collector resistor, let's see what value would be optimum to maximize the output amplitude. So we can determine the voltage that can appear on the load under two different conditions. On the one side, the maximum value, which is equal to the supply voltage minus the voltage drop on the output capacitor, times the collector to load resistance ratio, and in a similar fashion, we can determine the minimum voltage that can occur on the load by subtracting from the voltage found on the output capacitor the minimum collector emitter voltage that we can get, which we can set to about 1 volt to keep the circuit in the linear operating mode, and subtract the voltage on the emitter capacitor, which we already set to 1 volt. So now we can specify that the minimum output voltage is equal to the maximum output voltage, and to keep things simple, we can also specify that the load resistor is equal to the collector resistor. So from this, we can determine that the voltage drop on the output capacitor should be equal to 4.6 volts. And from that, the static collector emitter voltage should be 3.6 volts. We can now also calculate the voltage on the collector resistor, and putting in the collector current, we can also determine the collector resistor should be 540 ohms, but I will be using a 510 ohm resistor since this is a value that I practically have. Now, to confirm that the circuit works, I created it in the circuit simulator. And other than the components that we've calculated, I also added in a set of resistors to bias the base. Now, first thing to check about this circuit is of course the DC operating point. So if we run the circuit, we can first of all check that the transistor is in the correct state. So the collector current should be 10 milliamps. We are getting 9.96, so that's good enough. And then we can look at the collector emitter voltage. So this was supposed to be 3.6, we got 3.9, so it's close enough. Other than this, we can also confirm the voltage drop on the emitter resistor, which was supposed to be 1 volt. It's 0.998, so again a very good value. And finally the voltage drop on the collector resistor, which was supposed to be 5.4, but it's 5.08. So because we have a slightly larger voltage drop on the collector emitter, we have a slightly smaller drop on the collector resistor. So far the circuit is looking good. Next, to analyze the circuit's behavior when amplifying AC signals, I prepared two variants. So the signal source, the load impedance, the various resistors and transistors are all the same. The only difference between the two circuits is the added emitter capacitor on the right side. The main reason to add this component is to increase gain. So the voltage gain is set by the collector impedance divided by the emitter side impedance. Now, the collector impedance is the same in both circuits. It's the collector resistor in parallel with the load resistor, about 255 ohms, but the emitter side impedance on the one side is about 103 ohms, so the external 100 ohm resistor plus the internal 2.5 ohm emitter resistor, whereas on the other side, if we consider that the capacitor's impedance is negligibly small, we are only left with the internal emitter resistor, so a total of about 2.8 ohms. Now, it is important to mention though that to get this effect, the capacitor does need to be dimensioned accordingly. So the impedance needs to be of small value at the frequency of use. So this capacitor at 1 kHz, the test signal, has an impedance of about 340 milliohms. So anyway, the end result is that the voltage gain on the left side circuit should be about 2.5, whereas on the right side circuit it should be 91. But what do we actually get? So if we run the circuit to see how it behaves, first of all, starting with the left side circuit, we've got our input signal, about a plus minus 600 microvolt sine wave, and the output signal is a plus minus 1.6 millivolt sine wave. So almost triple the input signal. Now another thing we can clearly observe at this point is the phase inversion in the output. The output signal is 180 degrees phase inverted in reference to the input, and well, this will come to haunt us a bit later on. But for now, we can go back to the other amplifier. So here we have about 200 microvolts of input signal, and because we have a completely different amount of gain, we have about 15 millivolts of output signal. So it's about 75 times larger than the input signal. But anyway, the gain is much larger on the right side circuit than on the left side circuit, because of the added capacitor. Now, to observe the circuit's behavior with large signals, we can go through multiple input values using a stepped parameter. So for that, I'm using multiple input values to inject into the circuit. And since the circuit on the right side has way more gain, the input signal is divided by a certain amount so that the two outputs can be more easily compared. So if we run the circuit, we can look at the signal from the left side circuit, the one without a capacitor, and the circuit from the right side that does have a capacitor. And first of all, we can see that both circuits are somewhat limited in their output range. But another interesting feature that becomes apparent is that the circuit with the capacitor, so the blue lines, start to have their sine waves a bit distorted, more obviously on the upper side. So this part of the input signal is not amplified as well as the bottom half. One way we can see what is going on is to check the instantaneous amplification of the circuit. So we can plot out the voltage ratio between output and input for the circuit without a capacitor, and the same thing for the circuit with a capacitor. And well, since the gain here is way larger, I also divided this by 30 to have a more comparable value. Now there are various spikes occurring, but if we zoom in, these spikes are occurring when the sine wave passes through zero, so because there's a bit of a phase shift, these differences occur. But regardless, what you can make out from all of this scribbling is that the gain for the left side circuit, the green one, is far more stable than the gain for the right side circuit, the blue one, which varies greatly up and down. Now if we add another plot plane and also plot out the collector currents, we can see that we are getting maximum values of gain when the current is maximum and minimum values of gain when the current is minimum. So the gain in both circuits varies, but the gain in the circuit on the right side varies far more dramatically. This is a bit of a concern because this ends up creating quite a lot of distortion in the output signal, and that's not a good thing. So let's see what's going on. To understand this behavior, we need to come back to how the gain of the circuit is set. Basically, it's the collector side impedance divided by the emitter side impedance. Now, the collector side stays stable throughout the operation. The collector resistor is constant and the load is constant. But on the emitter side, we have this internal emitter resistance, which is not a physical component, but rather a current-dependent effect. So as the emitter current varies, so does the internal emitter resistance, and from this the total gain of the amplifier varies. Now, just how bad this variation is will depend on two main factors. How much does the emitter current vary in the first place, and also how much of the total emitter impedance is the internal resistance. In the case of the circuit with the external capacitor, the capacitor in parallel with the emitter resistance is close to zero, so here the dominant gain setting element is the internal resistance, so any variation in this will have a large variation in the output gain, whereas in the capacitorless circuit, the external resistor is large in comparison to the internal resistance, so even if you do have a variation in this, the total gain value does not vary all that much. For this reason, it's quite common to insert the two-resistor circuit to reduce distortion. So this arrangement will partly help to control gain, but it will also help to reduce this variable gain distortion. Now, to get a better picture of the gain variation, we can analyze our previous circuits using an AC type of simulation, and then plot out the various types of gain. Now, just as a small remark, the AC type of simulation is a small signal analysis, so the effect of the input signal's amplitude is not visible here. We are strictly analyzing the gain around the operating point, so we can't see distortion or things like that. So I have the two circuits, circuit 1 without the capacitor, circuit 2 with the capacitor, and if we start off by plotting the voltage gain for the two circuits, we can clearly see that for the first circuit the gain is much smaller than for the second circuit, so having the capacitor does increase the gain at low frequency, but as frequency goes up, both circuits start to lose gain. Now, as it stands, the circuits seem to have gain, so the unity point is somewhere in the gigahertz range, which is not necessarily false, if you consider that the input signal is the signal at the input of the amplifier. However, to get a more realistic response, we can consider the input signal before the internal resistance of the signal source. So the input signal is a value 1, this is set through the signal source, and the value at the output is what you get after the internal resistance. So we can determine the gain of the two circuits, reference to the initial signal source, by simply plotting out their values. So these would be divided by 1, and that would be the gain of the amplifier reference to the initial signal. So if we do this, we can see that we have a far more realistic unity gain point at around 10 MHz. So we can rerun the simulation with a different frequency range just to get a clearer picture. Now again, our second circuit, the one with the capacitor, does have higher gain, and again we see that at high frequency both circuits end up being limited by the amplifying element, the transistor, and then the gain after a certain point is more or less the same in both cases. Another thing to observe is the effect of the capacitor itself on the gain. So if the impedance of the capacitor is not small enough, you don't get the same gain. So we can see this at the extreme left side of the graph. When the frequency is very small, the impedance of the capacitor is very large, and thus the gain also drops, since the equivalent impedance of the capacitor in parallel with the resistor is not a very small value. So this is why when designing this capacitor, it's important to take into account the smallest working frequency, so that you can get a constantly flat gain. Now, just as a side note, in the simulator, for the emitter capacitor, I'm using an ideal capacitor. But in real life, that's not really the case. If your amplifier is supposed to work over a wide frequency range, you need to consider the non-ideal behaviors of the capacitor. Its equivalent model, other than the capacitance, also has a non-negligible inductor, the equivalent series inductance, as well as a non-negligible resistance, the equivalent series resistance. For the audio range, an electrolytic type of capacitor is usually a good choice by itself, since the resonance frequency, the frequency above which the capacitor becomes inductive, is usually above the audio range. But if your amplifier has to work in the RF spectrum, this sort of capacitor will behave like an inductor. So here, a ceramic type of capacitor is usually used. You can of course combine the two and make an emitter network with both, but it is worth pointing out that at some point, the connecting trace itself will become a problem. So for very high frequency circuits, it's best to keep the emitter at ground potential and use some other way to perform DC stabilization. So don't really involve capacitors at all. If we now come back to our previous simulation, we can also analyze the current gain. So in green again we have the circuit without the capacitor, in blue the circuit with the capacitor. As before, the amplifier with the capacitor has higher gain, and again in both cases the gain drops and becomes more or less the same as frequency increases. Now this time the unity point is around the 70-80 MHz range. And finally, we can also compare the power gain of the two circuits. So if we consider that the input signal is at the input of the amplifier, the unity gain crossover is somewhere above 100 MHz, so slightly lower for the circuit without the capacitor, much higher for the circuit with the capacitor. But if we take the input signal before the internal impedance of the signal source, then both of our amplifiers have a unity power gain at around 20 MHz. So even though this type of amplifier can generate very high gain levels, in a practical use case, it's also the most limited type of amplifier when it comes to high frequency operation. Now, there are two main effects limiting gain at high frequency in a common emitter amplifier. On the one hand, the collector base capacitance, and on the other, the input impedance variation. Since the collector is 180 degrees phase shifted in reference to the base, the output, the collector signal, is coupling back and attenuating the input, the base signal. And this effect becomes more pronounced at high frequency as the collector base capacitance's equivalent impedance starts to drop. This ends up reducing the input impedance and thus attenuate the input signal. A secondary effect that this causes is that high frequency reverse isolation is also bad. More signal can couple back from the output to the input, which has a negative impact on stability. So, final thing to look at is some network parameters. For this again we need an AC type of simulation, but we also need to add in the .NET statement in which we define the output load and the input signal source. So I added these statements for both circuits, and if we run the simulation, first of all we can look at the input impedances of the two circuits, and what we can see is that the input impedance of the circuit without a capacitor is much higher than the input impedance of the circuit with the capacitor. So the green line is the circuit with the emitter capacitor. The main reason for this difference being the fact that the input impedance is defined on the one hand by the base resistor network, which is the same in both cases, the transistor gain, which is again the same in both cases, but also the emitter impedance, which is not the same. So for the left side circuit we have the 100 ohm resistor, whereas for the right side circuit we have a very low impedance because of the capacitor. Now as frequency increases, we see that the input impedance will drop. This will cause an attenuation in the input signal. So even though the circuit can amplify the input signal, if it's coming through a very large input impedance, then the signal will be highly attenuated to begin with. If we now look at the output impedances, we can see that these are more or less the same for both circuits, because this impedance is mainly impacted by the collector impedance, which is the same 510 ohm resistor in both cases. So that's why this output impedance is fairly stable and more or less the same for both circuits. In the end, the common emitter amplifier is a widely used circuit mainly because it can provide both voltage and current amplification, and because of the very large values of gain it can provide. But just because you can get a lot of gain does not mean that you always should. Depending on the implementation, this might end up causing a bit too much distortion. Other than that, it's an inverting amplifier that usually has high input impedance and moderate output impedance. So if any of these features are something that you need in your design, this is a good amplifier topology to consider. Now, the simulations look good, but next time we will also check out a practical circuit. So for now, hope you got some useful information out of this. Leave your thoughts in the comments. Thank you for watching. Make sure to subscribe to get updated on my latest videos, and see you next time. Bye bye.